Secondo me la matematica è un lavoro. Sono contenta di poter dire che è un lavoro, che è il mio lavoro e che, diciamo, la mia passione e il mio lavoro coincidono ed è una cosa molto bella e secondo me non banale.
It is 2017 at the Mathematical Institute of the University of Oxford. Cristiana De Filippis, a first-year doctoral student, hears about a problem in Schauder theory, a highly complex branch of mathematics dating back to the 1920s that has remained unsolved for 20 years. She is advised to avoid this problem as it has stumped experts for 2 decades. She learns that Giuseppe Mingione, a renowned mathematician at the University of Parma, spent years on similar ideas, but eventually set the problem aside when the math would not work out.
And this is, let's say, a nonlinear Schauder method. So this, for the degenerate case, can be found, for instance, in the thesis of Manfredi.
For a young PhD to take on a problem that had defeated senior professors seemed almost like career suicide. But Cristiana does not believe in giving up, so she decided to tackle it anyway. Late at night, she opens her laptop and contacts Mingione directly. During a Skype call, she explains that she has her own ideas and wants to pick up where he left off. This meeting quickly changes the course of both their careers. Mingione later remembered how strong her presence was. She was like a force of nature. It was like a time machine, he said. Hearing her ideas felt like meeting his younger self from 20 years ago, knocking at the door of his own mind. This is the story of how a young mathematician brought a stalled field back to life and gave new momentum to an area that no one managed to crack open for 20 years.
Already great success.
Well, let's say that from my point of view, this is rather an easy spot because mathematics is essentially very democratic in the sense that it is cheap to do. You just need to have ideas and a piece of paper.
To most people, becoming better at mathematics means gathering as much knowledge as possible, knowing more equations, memorizing more formulas, and calculating faster than anyone else. But at the highest levels of theoretical mathematics, true talent often looks very different. It is about seeing less, not more. The skill lies in working through the noise until the real essence of the problem becomes clear. This is where Cristiana's strength lies. In her way of thinking, there are no sudden moments of inspiration or bursts of excitement. Instead, she has a rare and valuable skill. She can look at a complex maze of estimates, inequalities, and clues, and ask if there is a simpler way to see the whole problem. Kuusi, an exceptionally highly cited professor at the University of Helsinki who shifted from engineering to pure mathematics after falling in love with analysis, regularly collaborates with and debates Cristiana. He described the experience of bringing her a highly complicated proof full of what he called horrible details. Kuusi would show her a 10-page proof full of complexity meant to force a solution. Cristiana would look over the logic, spot what was not needed, and suggest a much simpler way. Why don't you just do it like this? The problem she chose was a historical problem based on Julius Schauder's work from the 1920s and 1930s. Schauder's regularity theory helped mathematicians understand when solutions to certain equations are smooth. In ideal conditions, if the input data for an equation are smooth, the solution will also be smooth. Classical Schauder theory is like a high-quality camera lens on a perfect day. If the scene is smooth and the light is steady, the picture is sharp. The math models work smoothly, producing predictable, stable results. But the real world is rarely so simple. Physical materials are often uneven. Heat might move easily through one part of a substance, but act differently at a boundary. A fluid can be predictable in one spot, but become turbulent just a short distance away. lava, porous rocks, human tissue, advanced materials, and complex fluids do not follow simple rules. Describing these messy situations leads to complicated equations, especially something called nonuniformly elliptic equations. These equations describe systems whose behavior can change significantly depending on where you look or how intense things are. Simply put, the equations are not broken. The world they describe is just rough. The main question is whether the math can still show that the solution behaves predictably, even amid all the chaos. Before her work, mathematicians used standard perturbation methods, such as freezing coefficients and comparing original solutions to simpler problems. But these classical methods failed completely for non-uniformly elliptic problems. With the stakes clear and the limits of past mathematics exposed, the field was stuck, looking for someone to break through a theoretical barrier that had stopped experts for decades. Cristiana comes from Bari, a coastal city in Italy. She grew up in Matera, a historic city in southern Italy known for its cave dwellings carved into the rock. She went to a local science-focused high school in Matera. For her, math was never about pressure, grades, or later plans. It just felt natural. In a long interview with the Italian math magazine Mad Maths, she was asked why she chose to study mathematics. Her answer was simple. She chose math because it was the subject that came most easily to her at school. She compared it to studying Latin, saying the two subjects felt similar because they both rely on rules, structure, and logical steps. She never pictured herself as a professional mathematician when she was young. She even joked that, at first, she did not know mathematics could be its own university degree. She thought math was just a tool for subjects like physics or engineering. When she found out someone could spend their life studying math itself, she was thrilled. She showed her early talent on her own. As a teenager, she became fascinated by synthetic geometry problems. In these classic exercises, you start with a simple triangle, add some complex elements, and then try to prove a hidden fact within the drawing. Before any university training, solving these geometry puzzles on her own was a game to her. To pursue mathematics seriously, Cristiana had to leave southern Italy. Following advice to study at a northern university, she enrolled at the University of Turin for her bachelor's degree. She lived at Collegio Einaudi and found herself in a new academic setting. She graduated in 2014 under the guidance of Susanna Terracini. After Turin, she moved to the University of Milano Bicocca for her master's degree, which she completed in 2016 while working closely with Veronica Felli. She was not sure what kind of mathematician she wanted to become. In her last year of high school, curiosity prompted her to buy Herstein's classic algebra book, and at first, she was drawn to that field. While studying in Milan and going to lectures by experts such as Arrigo Salina and Sandro Salsa, she noticed she was drawn to a particular type of problem. She was interested in questions about continuous change, boundaries, and energy, but did not know which branch of mathematics they belonged to. She explored various areas, including differential geometry and mathematical physics, to determine where her interests lay. Eventually, she realized her interests lay in the field of mathematical analysis and variational principles. She later described the feeling of finding her academic home as, "and here I am." Variational problems have their own language. They ask what shape, path, or state nature chooses when it tries to minimize something, such as energy, distance, effort, or tension. This is the science that explains why soap films form certain shapes, why turbulent systems reach equilibrium, and why materials bend under stress. Finding this field gave her a clear direction. She was ready to go. After earning her master's degree in Milan, Cristiana wanted to test her capabilities in a real research setting. She went to France for an internship at INRIA Sophia Mediterranee, a well-known research institute in the Sophia Antipolis Technology Park. There, she began working closely with Paola Gotin, a respected mathematician specializing in hyperbolic conservation laws. Together, they wrote Cristiana's first mathematical paper. Their work focused on global well-posedness for weak entropy solutions of bounded variation in scalar conservation laws with non-local flux. They proved convergence using a modified Lax-Friedrichs algorithm, achieving a technical result in one spatial dimension. For the next step in her career, Cristiana needed a place that matched her ambition. She moved to the United Kingdom to start her PhD at the Mathematical Institute at the University of Oxford. She focused on partial differential equations and worked directly with Jan Christensen as her supervisor. Oxford gave her the intellectual environment she needed to thrive. She has said that her doctoral years there gave her complete freedom to work around what truly interested her. Christensen was an ideal advisor. With his support, she traveled widely, met international researchers, and built collaborations both within and beyond her group. Thanks to Christensen's professional connection with Giuseppe Mingione, Cristiana was introduced to the University of Parma. Parma had a very active group focused on analysis and regularity theory. Partial differential equations, or PDEs, are the language mathematicians use when many things in a system change at once. To track heat moving through a metal, fluid pressure, material stress, or the shape of an object in balance, you need PDEs. In this field, regularity theory asks whether the solutions to these equations are smooth and predictable, or become rough and chaotic.
Al momento sono un ricercatore tenure track all'Università di Parma in analisi matematica e mi occupo di regolarità per minimi di funzionali del calcolo delle variazioni per soluzioni di equazioni differenziali alle derivate parziali ellittico-paraboliche.
When Cristiana first learned about the stalled effort to extend Schauder theory to non-uniformly elliptic equations, she was advised to walk away right away. Do not risk your limited time, your need to publish, or your early career on a problem that is just too hard. Many talented people have spent years on equations that never gave in. But she decided to ignore the warning and reached out to Giuseppe Mingione anyway. Mingione had dedicated years to working on similar ideas. He and his collaborators found a threshold condition that appeared to indicate when regularity should hold, but the final proof had resisted all his efforts. The main challenge was controlling the gradient. The gradient tells you how quickly a solution changes from one point to another. If the gradient grows too much or in an unstable way, the entire solution becomes unreliable. Because the system is non-uniform, the gradient cannot be computed directly using standard methods. To get around this problem, Cristiana and Mingione created what they called a ghost equation from the source. This was a simpler version that exposed hidden information without causing the main equation's variables to become chaotic. The proof meant pulling out this hidden information bit by bit. They had to break the gradient into specific parts, estimate the limits of each, and make sure no small mistake ruined the final answer. Cristiana called this difficult, repetitive part of the work an unending game. Their result was a shock. Simon Nowak, a renowned mathematician in the field of non-local systems, reviewed their work and called the method far-fetched, but beautiful. It was an approach that looked nearly absurd in its ambition until the math actually checked out. She earned her PhD from the University of Oxford in 2020. That same year, she received the Gioacchino Iapicino Prize from the Accademia dei Lincei, which honors outstanding work within mathematical analysis by researchers under 30. Following her postdoctoral work at the University of Turin, she formally joined the faculty at the University of Parma in 2021 as an assistant professor. By 2023, the Italian Mathematical Union awarded her the Bartolozzi Prize, and she was elected as a fellow of the inaugural cohort of the European Mathematical Society Young Academy. In 2024, she won the European Mathematical Society Prize. The EMS Prize is among the most prestigious honors for young mathematicians in Europe. Cristiana received this prize for her outstanding work in elliptic regularity, especially her Schauder estimates for non-uniformly elliptic equations and related variational problems. In 2025, she was awarded the SIAM Activity Group on Analysis of Partial Differential Equations Early Career Prize. Furthermore, she achieved the rank of full professor of mathematics at the University of Parma in 2025, a stunningly fast ascent through the Italian university system. She also secured a massive European Research Council starting grant, providing heavy financial support for her research program from 2026 through 2030. Even with the pressures of publishing, peer review, and international lectures, she often talks about keeping a normal, grounded life outside her math career. In interviews, she says she copes with the mental demands by running every weekday morning. She also loves riding horses and keeps one in Matera, which helps her stay connected to the land she grew up in. In her free time, she steps away from math. She enjoys reading, listening to music, and especially likes the classic Italian Western comic Tex Willer. She also has a cat. She doesn't take herself too seriously. During an EMS magazine Zoom call with Tuomo Cusi and Raffaella Mulas, halfway through the interview, her phone battery got low. She quickly left the video call, then came back a moment later, sitting on the floor under her table to plug in her phone. Cusi laughed and asked why she was under the table during a formal interview. She joked that she just wanted to give everyone a different perspective. She is one of the breakthrough stars in mathematics today, and we look forward to following all she will achieve in her career.